Okay. Before starting class, do you have any question? Okay, so if you do not have, then I'm gonna start in here. So right now we are discussing about non-ideal characteristic of PN junction diode. In here is as a second effect. We're gonna discuss about so-called high-level injection. Okay. So the definition of a high-level injection is this one happens when you apply forward bias. Okay, so when you apply the forward bias in the PN junction diode, so as we discussed, when you apply the forward bias in the PN junction diode, as you remember, by applying forward bias, we reduce the barrier height. So in the P side, you have lots of holes. They start to inject it to the N side. And in the N side, you have electrons. They start to inject to the P side. Okay. So when this one is happen, as this figure is described, in the P side, for example, you have majority carrier, which is hole, and then you have minority carrier, which is electron. In the N side, majority carrier going to be electron, and then the hole going to be minority carrier. Okay. Now, when you apply the forward bias, as we discussed, from the thermal equilibrium value of the minority carrier, now is the number of this carrier concentration going to be increased. Okay. And then, as you know, the exact increase this one, for example, following that the PON exponential QVA over KT, right? So using this equation, we have this increase of this minority carrier concentration. Now, as you can see from this equation, as we increase the VA, okay, the concentration of this minority carrier are going to increase exponentially, right? So which means that if we further increase the voltage, now is, as you can see, your carrier concentration going to be further increased, okay? And then we're going to have a situation at the certain voltage when the VA reaches to this high-level injection. Then what happened is the number of minority carrier concentration, for example, in the N side in here, the number of hole concentration in here, which represent the minority carrier, is start to comparable to this number of majority carrier concentration. So in our book is that when you say comparable, that means that when the PON reach to the close to the 10% of its majority carrier concentration, then now is that we define as the device reached to the high injection or high level injection. Okay. So that definition is that we call the high injection. So again, from this definition is that you can obviously calculate the exact applied voltage which induced this high level injection. So for example, let's say in the N side, if you have 10 times 17, okay, the doping level, okay, if you have N psi with ND with this doping level, then as you know from in here, NON will be close to this 10 to 17. Okay. Now PON you can calculate from the Ni squared divided by ND. So this is going to be 10 to 3. Okay. Now, if you plug in the condition, this new condition, actually this is not O, this is actually just a number. So Pn will be PON multiply exponential QVA over KT. Okay. Now that one equals 0.1 times NON. Okay. So you can plug in the NON in here. Okay. PON, we know that from in here, right? So as you can see from this equation, if you solve this one, then from there is that you can calculate this VA, okay, which represent the device reached to the high level injection. Okay, so that way is that you can identify at what forward bias you expect the high level injection for the given this doping level in the PN junction diode. Okay. So when the high level injection is that what happened is, so when we apply the bias, the carrier concentration will follow that now is this kind of formula. Okay. So following that the applied bias. Okay. Now when we have for this condition, if you look at the carrier concentration, in the end, the electron will have their thermal equilibrium value plus excess those electrons. Hole also same way, it has the thermal equilibrium value hole and plus their excess hole. Okay. Now, under the high level injection, NP, this one is following that using this one, then we can approximate this way. Okay. And then that related with our applied voltage with this relationship. Okay. Now, at the high level injection, those generated this electron and hole, those level, these level are comparable to their carrier concentration. So we can approximate with this equation with this. Okay. Then now is we can have is because generation these electron hole, they're in the same level, so we can approximate their concentration will follow that roughly with this formula in here. Okay. Now, if we look at in here, and then previously, when I look at this in the PN junction diode, the diode current is related with IS, and then as we discussed, exponential QVA KT minus 1, right? And then especially if you look back for the IS related with the material parameter, okay, in the PN junction diode, especially minority carrier concentration, okay? So in here, minority carrier concentration, this one, that related with the applied bias at the high level injection. So IS also related with this applied bias. And especially when device reached to the high level injection, then now is that related with exponential VA over 2 VT. Okay. So for that is now we get this kind of conclusion is when the device reaches to the high level injection, the current is proportional to this exponential VA over 2VT. Okay. So this one is affecting that when you look at the IV characteristic in the forward bias. At the forward bias is that when you look at the characteristic, especially in the very high current, your current is this one is does not follow that the ideal IV characteristic which we obtained in the previous chapter. Instead, this area at the high level, the voltage, the current related with this exponential is VA over 2 VT, following this curve in here. Okay? And then that's due to this high level interaction. Okay? Another thing is as a non-ideal characteristic, especially when the VA is very large. Okay? When the VA is very large, is in the previous case, we didn't consider about the finite resistance in the bulk area of the material. Okay, so when you form the p-n junction like this, and then when current flow through this device, especially when the current is very high, we need to consider is this low resistance area in the bulk material. Okay. So that the ideal case is that we have this kind of current versus voltage characteristic represented by our current related to the voltage like this. Now, if we consider this resistance in the bulk material, then we need to consider some voltage drop happens across this neutral region. Okay, so this one also need to be considered when the current is very high. So which means that when you look at again is current versus voltage characteristic of the p-n junction diode. At the very high current is that current is instead of following the linearly, not the linearly, exponentially increased. This one is VA over KT. Instead of following this one, now due to this finite resistance in the bulk area, the current is actually a little bit rolling down like this. Okay, and then the current does not is exactly followed by this applied bias. Some of the bias voltage is actually loose in the neutral region. Okay, so that also we need to consider, especially in the high voltage and the high current in the p-n junction diode. Okay, so that is the forward bias side in the p-n junction diode. Now is we're going to look at the reverse side in the p-n junction diode. So as we discussed is the IV curve, especially in the reverse bias. In the previous also we discussed that when the reverse bias is applied, instead of current is saturated with IS is slightly increased like this, right? Okay, so that one is we discuss as the when you apply the reverse bias, you have a generation current, and then that generation current is increased slightly as we increase the further reverse bias. Now, if we increase this reverse bias further and further, at some point we're going to see that at a certain bias, we will see that a lot of current flow, okay? And then that kind of dramatic increase of current, we explain as the so-called breakdown in this PN junction. Okay. So in the PN junction diode, we have the two different kind of breakdown we're going to discuss in the following slide. One is we call tunneling breakdown. Another one we call avalanche breakdown. Okay. The mechanism of these two breakdown, they are different. But overall, the effect is that when the device reaches to the breakdown, we're going to see that lots of current flow at that breakdown. Okay. So first is let's look at so-called tunneling breakdown. Okay. The basic mechanism of tunneling breakdown is actually described in the figure A in here. Okay. So for example, let's say in the semiconductor, especially when the electron travel in the certain energy barrier. Okay. So let's say if you have this kind of energy barrier exists in the conduction band, okay, in the semiconductor. So when you apply the bias, let's say electron moves from left to the right, okay, and then when this one electron see this barrier in here, is the most of the case is this electron doesn't have enough energy to overcome this barrier, so that it cannot flow through the structure. Okay. Now, at the special case, if this barrier width is very small, so when you say that very small is tenths of nanometer in here, then what happened is that the electron, this one is, instead of going over this barrier, now there is a probability this electron can pass through this barrier height. Okay, and then this probability we call the tunneling through this barrier. Okay, so by this effect is we can also see that the electron is basically tunneled through this barrier height if this W is very small. Okay, so that is the basic concept of this tunneling effect. Now, in a practical case, when you apply this concept to our PN junction diode, the tunneling can be happens as described in this figure B. Okay, so in the PN junction diode, okay, if we have some special case, in this case is that if the depletion width, this is the very small, is tenths of nanometer. Okay, if we can create it like this, then in the P side, the electron in here can directly pass through this depletion region and then contribute the current in the conduction band. Okay, so if this kind of condition meet, then now is we can see that the lots of current flow through this structure. Okay, so the key point in here is that we need to reduce this W. Okay, depletion width. Okay. So now depletion width, as we discussed in the previous class, this one related with is your doping and your applied bias. Okay, so for example, is the doping. Okay, so let me have a question to you in here. Okay, if you have the highly doped compared to the lower doped, this PN junction diode, which one has smaller this depletion width?
Would it be the lower dope with a smaller depletion region?
So one answer is Jamie in this one. Any other answer or objection? Correct answer is this one is highly doped. Okay, so one example, as you remember in the previous, is that when we discuss about, for example, it's a PN junction, and then when you look at this depletion width, so let's say this is the XP and this is XN, and then the P side is doped with Na, N side is doped with Nd, then you have this kind of relationship. Na multiply Xp equals Nd multiply Xn. Okay. So when you have a highly doped, then depletion width is getting smaller. Okay. So that kind of relationship we discussed in the previous class. So if you have a PN junction diode with a highly doped semiconductor, you can also have the very small this depletion width. Okay, so that's okay. That's good. Okay. So in the practical case, is the how we then make the very small this depletion width. So to do that is that this kind of tunneling breakdown can be formed with heavily doped PN junctions. Okay, so when you have a heavily doped PN junction, we can purposely make that this depletion width is very, very small. Okay, close to the tens of nanometers in here. Okay, and then for this case, we can actually promote this tunneling effect in this device, and then through this tunneling effect, especially when you apply the reverse bias, we can start to have the lots of current flow. So this one is the energy band diagram. This one is showing that this kind of structures. So when we have the very highly doped, so this is the kind of extreme case. This is the EV and this is the EC. Okay, and then this is in the P side. When you have the highly doped, your EF is the very close to EV, or sometimes if it's very high, it can slightly over this EV. Okay? And the same way in the N side, again, if you have very highly doped, then the EF is actually close to this EC. Okay. So for this case is that the initial at the zero bias, you're going to have this kind of condition. Okay. Now, when you apply the forward bias, in this case, if you look at in here, is below this Fermi energy level, as we discussed, you have lots of electrons. So in this case, is that at the forward bias, again, directly from the n-side electron can going into the this p side, so that it can flow the lots of current in the forward bias. At the same time, is when you apply the reverse bias, we're going to have also condition is that as we increase the reverse bias, at some point, the electron in the p side, they're going to directly see that the empty state in the n side, okay, on the conduction band. Okay. When this W is small enough, in this case, those electrons directly pass this depletion region and then start to flow the current. Okay. So in this case, when you look at the current versus voltage characteristic for this device, when you have the reverse bias, you're going to start to have the current, and then at some point, when the condition meet for this case, then you're going to start to see that this breakout in here. Okay. Theoretically, is that this tunneling current can be theoretically formulated with a certain approximate. In here is we do not actually calculate derive this equation, but you can just assume is theoretically we can also calculate, okay, as a function of so-called this electric field through the junction. Okay, and then when we define that this threshold voltage, okay, the breakdown voltage we can define as the when the current, this tunneling current is close to the 10 times of their leakage current. At that point is we define as this breakdown voltage. Okay, and then again this breakdown voltage, as you can see, depends on the doping level. So in other words, for this tunneling breakdown, we can adjust the doping concentration in the PN junction diode, and then from there we can adjust this breakdown effect. Okay, so this kind of device is using this highly doped semiconductor. That is, we call the Zener breakdown device. Okay, or Zener diode we call it. Okay, so for this device, we can actually set when the reverse bias reach to the certain level, that start to flow the lots of current. Okay, and then later on, I'm going to show you as an example, this kind of device especially is very useful to form voltage regulator, which actually prevent that or regulate at the certain voltage level in the upper side. Okay, so that is the basic mechanism for this Zener diode. Okay, and then this diode again is affected by the temperature. So typically, when the temperature is going up, we expect that the energy gap is slightly lower. So that affect your tunneling current is increased. In other words, is that this effect affect your breakdown voltage is getting lower. Okay. Another type of breakdown, this is a more general case for this semiconductor material, which is called avalanche breakdown. Okay. The basic mechanism of avalanche breakdown is we have, for example, this PN diode. Okay. When you form the PN diode, is we have the depletion region. Okay. Now, especially in the PN junction diode, when you apply the reverse bias, okay, when you apply the reverse bias and then increase this reverse bias, we're going to start to see that the electric field, okay, electric field within this depletion also increased. Okay. So now, for this condition, at some point, minority carrier, which, for example, in the P side, N side hole, due to this electric field, when they going in to this depletion region, they start to accelerate through this electric field. Okay, so in other words, that because electron hole, they are charged, right? It's electron negative charge, hole is positive charged. Okay, so when they see this electric field within this depletion region, they're gonna guided by this electric field. Okay, And then when this one is guided within this electric field, by this electric field, they're going to be accelerate, okay, through this depletion region. Okay. So when they accelerate, at some point, they're going to have enough energy so that when they hitting those electron hole, hitting the silicon atom, then some of the electron hole, which initially bounded by the silicon due to the attraction force, they can be free by this acceleration energy they get from this another electron hitting them. Okay, so then now is you can actually free additional electron hole. Of course, the electron hitting those electrons hole, they lose the energy, right? But by this process, you can actually generate more electron holes within this depletion region. Okay, and then that kind of process is we call the impact ionization in the semiconductor. Okay. Theoretically, we actually formulate this impact ionization with the so-called ionization rate for the electron and the holes. Okay. The definition of this ionization rate is that when we have the certain given electric field is going into the structure, how many electron the hole pairs can be generated due to this ionization. Okay, that is described by this factor. Okay, so when this kind of ionization happens through this depletion region, actually this mechanism can initiate so-called this avalanche breakdown. Okay, so for example, this one is just to formulate the descriptive the image in here. So for example, in the PN junction diode, you have a depletion region which has the electric field. Okay, so in here is that you have electric field is going in like this. So when the electron is somehow, let's say, going into this depletion region, okay, so electron is negative charge, so that's going to be accelerate through this structure in here. Okay, now when they accelerate, at some point, let's say this electron hitting to the body of the silicon, and then that give the energy to the silicon, and then silicon is free the electron hole. Okay, then you generate the electron hole. Okay, now still this generate the electron hole, and then the previous electron, they are within this electric field region, so it still is accelerate. Okay, so while this one is accelerate, again that can hit the body of this silicon atom, and then free additional electron hole pairs. Okay, so when this process keep going within this the structure depletion region, then you're going to expect something like this: is one electron going in, but at some point you're going to free up the multiple, and then that going in further, and then you're going to free up the additional. So this kind of thing is multiplied many, many times, so that you're going to start to see at the end lots of current flow through the structure. So initially, it just starts one electron, but at the end, when the electron hole coming out from this depletion region, we're going to start to see lots of electron hole movement, and then that consequently affect lots of current flow. Okay, and then that is we call the avalanche breakdown. in this semiconductor. Okay. So in the avalanche breakdown, another parameters we also interest is that is the M parameter which represent multiplication in this process, which calculate from that the initial current, okay, and then look at the output current. Okay, so by looking at this ratio, we can define this M parameter. Okay, and then theoretically, this M parameter related with the breakdown voltage. So when you increase the reverse bias, and then reverse bias is close to this breakdown voltage, we're gonna start to see that this M parameter is dramatically increased. Okay, and then that one theoretically formulate with a dedication. So if we just use the previous our discussion in the PN junction diagram, for example, is that this one represent the electric field is the maximum electric field. We can calculate using this equation. Okay? So this one is, as we discussed, let's say if we look at the PN junction diode, is a PN diode, and then look at the electric field strength. Okay, as we discussed, just assuming that let's say step junction PN diode, electric field follow that this kind of curve. Okay, and then as you remember, Emax happens in the physical junction. Okay, and then if we borrow the formula for the Emax, that will follow this equation in here. Okay, and then let's say if we assume that the PN diode is p-side highly doped, this PN diode, then we're going to have this kind of condition in here. And then Emax is now further simplified with this equation. Okay. And then from in here is that we can roughly approximate is this Vj represent is that actually VBI minus our applied bias. Okay. And then this is a reverse bias. And then typically this VA for this breakdown is much bigger than the VBI, the magnitude. Okay. So from there, we can approximate is that when device reach to the breakdown, okay, electric field max is reached to the so-called critical electric field. Okay, so each material has defined the critical electric field, which described this ionization effect in the material. So based on that material parameter, if you plug into this simple equation, then you can approximate is for the P plus N diode, your breakdown voltage going to be this equation. Okay, so based on the doping concentration of the P N diode. Okay, so that way is also you can estimate this breakdown voltage. Okay, so in a typical case, when you look at this two different type of this breakdown, the avalanche breakdown typically happens in the very large the voltage compared to this tunneling breakdown, which represent the general breakdown device. Okay, so that is typically is we saw in the device. Okay. So as a last comment before we end this section, in the practical application, this kind of breakdown, the PN junction diode, can be used for, as I mentioned, voltage regulator. So for example, this is a very simple circuit using this Zener breakdown device. Especially Zener breakdown in here is that we put as the such a way so that when you have, for example, input signal going in here, okay, and then you're gonna only look at the output. Okay, so let's say in the practical case, let's say you have the input signal is fluctuate, is let's say 10 to 12 volt. Okay, now in the output is I want to always have this one as the around 10 volt. Okay, so to regulate this one, if you choose the breakdown voltage is 10 volt for the Zener breakdown, connect such a way like this, then when the voltage is high, okay, then now is that the Zener breakdown resistance is going to be small, so that the most of current is flow through this structure. Okay. When the voltage is small, now over there, across this Zener diode, the resistance is going to be very high. So then is current flow through this output. So by that way is that we can actually regulate the output voltage to this Zener breakdown voltage. Okay. So this is the kind of one example of how we use this breakdown effect in the PN junction diode. Okay, so that's good. Any other question for before we move to the next? Okay. If you do not have any other questions, so then let's move to the another one. Okay, so in this section is that now we're going to look at the capacitance of this PN junction diode. Okay, so when you look at the PN junction diode, we have two different types of capacitance we discuss for the PN junction diode. One is we call the transition capacitance, or this one is same way, is that we call the junction capacitance. Okay, and then I'm gonna explain later on the detail. So that is the one type of capacitance. And another capacitance we notice in the PN junction is called the storage capacitance, or sometimes we call the diffusion capacitance. Okay. So we have these two types of capacitance exist in the PN junction diode. So first, the junction capacitance, okay, or is we call the junction depletion capacitance. Okay. The basic concept of this capacitance coming from the concept in the depletion region. So when you look at the depletion region in the PN junction diode, as you know, is that in the depletion region, electron hole mobile carriers they start to recombine. So they leave those ionized charges within this depletion region. So in the P side, hole is moving to the N side. So that leaves the negative, this ionized charge. Okay. So similarly, if you look at the N side, electron is moving and recombine. So within the depletion region, that leaves this positive ionized charge. Okay. And then as we discussed previously, this ionized charge, they are coming from their dopant. Okay. So they cannot actually move within the crystal structure. Those dopant is actually bounded within the crystal structure. Okay. So in other words, when you look at the structure in here, this structure is, as you can see, is a positive, negative charge. They are actually separate in a space. Okay. This concept is very similar to the typical this plate capacitance. Okay. So in the plate capacitance, as you know, is we can form the capacitor is by using the certain insulator material between the two electrodes. Okay. So when you have this kind of structure, as you know, through this insulator, those charges cannot pass. Okay. So when you have the certain applied bias, okay, you have this physical separation of the charge exists. Okay. So this PN junction diode is, in some sense, is very similar to this typical plate capacitance. Okay. So based on this concept, is that we can actually look at the capacitance within the junction can be approximate with this kind of equation in here. Okay. So Cj represent the junction capacitance. Okay. W represent the depletion width, okay, which describe that the PN junction in here. Okay. A represent the cross-sectional area of this PN junction. Epsilon 0 represent the dielectric constant in vacuum. Okay. And then the Ks is, this is the permittivity for the material, relative permittivity in the material. Okay. So for example, in the silicon, this value is around 11.8, right? So using this general formula, we can approximate this junction capacitance in here. Okay. And then this one is basically determine that this junction capacitance. Now if we further include some parameters for this junction capacitance in here, W, this is, as I mentioned, depletion width. So in the previous chapter, as we know, depletion width related with our doping, and then you applied bias. Okay. So we can plug in that one in here. Then we can approximate this junction capacitance with this equation in here. Okay. And then finally, with this equation. Okay. So now this is the interesting point in here. Okay. If we have a PN junction diode, okay, if we have a PN diode, okay, we can actually measure this capacitance in the PN diode for the different bias. Okay. So when you measure this capacitance and plot the those values as a function of voltage, then we can actually get this kind of curve in here. Okay. So let's choose this one of Cj square. That's the take y-axis, and then the VA applied bias is that the x-axis like this. Okay. Then, as you can see, when the VA close to the VBI, okay, now this value is 0, so you can have the 0, this 1 over Cj square. Okay? And then when we increase the VA, the capacitance value will follow this line. Okay? And the slope of this line is, as you can see, determined by this value. Okay? Now, in here is we can have an interesting point is we can make from this measurement. One thing is by just measuring this capacitance versus VA for a given PN junction diode. Now, when we measure this intercept point for the voltage, that voltage give us that our VBI value in the PN junction diode. Okay, so that is the one thing is we can obtain in here. And then when you look at the slope of this curve, that slope depends on your doping concentration in the PN junction diode. So as you can see, the slope in here related with the 2, Q is the charge, okay, epsilon 0 and then Ks that represent that this is a material parameter, right? So for example, if we have silicon, those Ks and epsilon 0, they are all fixed value. Okay. Only variable in the PN junction diode going to be this doping concentration. Okay. So for example, if the doping is a constant throughout this PN diode, then now you're going to have this kind of constant slope throughout this structure. Okay. And then from there is that we can also roughly estimate what will be the doping concentration profile in the PN junction diode. So that kind of information is we can obtain by this junction capacitance. Now, second capacitance is we call the storage capacitance. So storage capacitance, especially this one, happens when we have injection of minority carrier in either side. So which means that when you have a PN diode, okay, so when you have PN diode, when you apply the forward bias in the structure, hole is injected to the N side, and the electron is injected to the P side. Okay. Now, when those electron hole injected to this opposite side, that create the additional charge is within this structure. So, for example, this curve is that roughly show the excess those carrier concentration at the outside of this depletion. So when you apply the forward bias, as we discussed, carrier concentration is exponential decaying, something like this, right? And then this increase of this charge create the so-called storage capacitance. Okay. So theoretically, we can also derive this capacitance following this step in here. Okay. So for example, let's say if the contact, okay, outside the contact, so you have, let's say PN diode, okay, and then this is the depletion region. Okay. Let's say you have a certain contact, electrical contact in the outside. Okay. If this contact is very far from this junction edge, depletion edge, okay. Now, then from there, we can approximate the carrier concentration as the exponential decay. Okay. So for example, if we look at the N side, Wn is much larger than the diffusion length of the hole. Okay. Then from there, hole concentration will follow that this exponential decaying, okay, as a function of this x prime. Okay. Now, to calculate the total number of charge exists in this neutral region in the N side, we're going to just integrate this from the depletion edge to the all the way. Okay. In here cases, let's just choose the x prime is very large value in going into infinite, and then we plug in this equation in here, and then we integrate all this area. Then from there we can obtain the total number of charge. Okay. So same number of charge is, as you know, is induced in the opposite side. Okay, in the p side. Okay. Now, then we're going to have the conclusion of the charge going to be this equation. Now, the capacitance, by definition, capacitance defined by this one. When you have a derivative of the charge, change with your applied bias, that determines this capacitance. Okay. So in here, we define this charge as the storage capacitance. Okay. And then we have the derivative of QB to this applied bias, VA. Okay. So if you do, then from there is you will get this kind of formula in here. Okay. And then this one described as the storage capacitance in the PN junction diode. Now, in here is that we have important thing is we have to keep in mind. In the PN junction diode, is you have PN diode. You have when you have a depletion region in here, okay, that one is always created this junction capacitance. Okay. So in other words, this depletion region is going to be exist when the device, of course, apply forward bias and also reverse bias. So in other words, the junction capacitance exists in both forward bias and reverse bias. Okay. Now, when you look at the storage capacitance, the origin of this storage capacitance coming from this injected charge. Okay. Now, this injection of the charge only happens when you apply the forward bias. Okay. So in other words, this storage capacitance only exists when the PN junction diode applied by the forward bias. Okay. And then when we look at the magnitude of this capacitance, especially in the forward bias between the junction capacitance and storage capacitance, we can see is this value for the storage capacitance is much larger because it's exponentially increased. Okay. So that kind of conclusion we can get from this slide. And then another parameter is also I want to point out in here is especially when you look at the device as the electronic device. We also look at the so-called small signal the model for the device. So small signal model means that the device is that, let's say, if you have the PN diode, or later on is when you have the transistor, typically there is a certain bias voltage applied to the device. At the same time, over there, we impose that very small, the input voltage is there. Okay, and then this input small voltage that contains the, let's say, certain signal. Okay. And then we look at how this signal is actually goes through the device and then generate either current and voltage at the output. So for that purpose, in here is that we also define as the so-called small signal resistance. Okay. Small signal means in terms of device for PN junction diode, if we look at the PN diode characteristic as the, let's say, this curve, then if we have the certain bias located in this location, now on top of in here, we have some modulation of the signal. Then that's going to modulate in here and generate the corresponding this current. Okay. And then this slope in here between the current and the voltage, that defined as this small signal resistance. So simply is that this resistance is in here is in terms of conductance is one of a resistance in here that will have this kind of relationship. Okay. And then the current ideal case diode is following this equation. So from this relationship is we can obtain this is a conductance value for the PN junction diode. And then from there is that you can obtain the resistance value. So resistance, small signal resistance, we can obtain from this equation in here. Okay. Now, when we look at the small signal resistance, especially in this case is in the forward bias, right? But when you look at the small signal resistance, look at in the reverse bias in the PN junction diode. As you remember, in the reverse bias, you're going to have this kind of curve in the PN diode. Okay, and then open this one related separate with saturation current. Okay. For this case, as you know, even though you have lots of voltage change in here, the current change does not change. Okay. So in other words, this one translates as the small signal, this resistance, going to be very large value, okay, in the PN junction diode when device applied by the reverse bias. So this is the kind of summary for the so-called small signal equivalent circuit model for the PN diode. So for the PN diode, we split it as the reverse bias condition and the forward bias condition. So in the reverse bias case, it's the PN diode we can approximate as it has the reverse bias, this resistance in the PN diode, and then you have a junction capacitance across this PN diode. Okay, and then in the outside, you may have some contact resistance can be exist in the outside. Okay. So we can draw the small signal model for the PN junction diode in this way. Okay. Now, when you apply the forward bias, you're going to include the additional capacitance to this model. That is this storage capacitance. So by adding the storage capacitance, now you're going to have this parallel storage capacitance with this small signal resistance. Okay. So by this way is that you can actually draw the equivalent circuit for the PN junction diode. Okay. So far, do you have any question? Is it too fast or is it okay?
It's okay,
I think it's
Professor.
okay. Just a
Okay,
lot to
then that's
go back. I just go back to the lectures.
okay. Okay, then that's good. Okay. Now is that I'm gonna also describe that the so-called short base diode. Okay. This is the name of the diode which has the special this kind of configuration. So for example, if you have the P plus N diode, and then especially in this load of this side, the length of this neutral region is a very short case. That's we call the short based diode. Okay. When we say that very short, this one is the criteria of the short means that for this particular case, you have an N side and the minority carrier going to be whole. So when you look at the diffusion length of hole, and then compare this one with the contact location, so from this junction edge to the outside of this electrical contact, that distance we define as a Wn. Okay. Now, if we compare this LP and the Wn, okay, and then when the LP, this one is much larger than the Wn, then now this one is we call the short base diode. Okay. So that's the meaning of this short in here. Okay. So the short, the meaning is arbitrary, but the concept is LP is much smaller than, much larger than the Wn. That's the case is the short base diode. In other words, is that this contact location is very close to this junction edge. Okay. So that is we call the short base diode. Okay. Now, when this one happens, especially when you look at the hole concentration in this N side, the hole concentration going to be, instead of exponentially decaying, we can approximate that this concentration is almost linearly decaying. Okay, so this one is actually in the previous class, we actually derived when the LP is much larger than the Wn, and then when the LP is much smaller than the Wn. So we have these two cases, and then we derive this distribution of this hole. Okay. So when the LP is much larger, in other words, Wn is very close to the junction, the conclusion that this hole concentration going to be linear. Okay, so linearly decaying like this. When the WP is much smaller than the Wn, or Wn is much larger, it's separate a lot from the junction, then as we know, this hole concentration is exponential decay. Okay. So those two is actually we studied in the previous class. Now, for the short base diode, is a particular interest is that when the Wn is much close to this junction. Okay. For that case, is now is you can have the concentration in the lower doped side, minority carrier concentration going to be linear in here. Okay. So that is the one thing is that we discussed. Another one is, as you remember, is that we also discussed about the total current, okay, in the PN junction diode. For the PN junction diode, total current going to be hole current plus electron current. Okay. Now, if you remember, is that when you discuss the ideal PN junction diode, okay, you may remember that this kind of curve. Okay, so this is the current represent, and then this is a depletion edge. Okay, and then when you calculate the current, okay, especially let's say P plus N junction, we start with the minority carrier concentration. So in the P plus, minority carrier concentration is electron, okay, and minority carrier concentration is a hole. Without any bias, you have thermal equilibrium value like this. Okay. Now, when you apply the forward bias, for example, carrier concentration is increased like this. Okay. And then that's the ways that we obtain, that is the curve. Okay. Now, in a similar way, when you look at the current, now is based on this carrier concentration, we actually using the diffusion equation for the current, and then we obtain the current. So in a short, the current will follow the similar pattern of this minority carrier concentration, so that we can have the distribution of something like this. Okay. Now, what I point out in here is that when you look at the total current, okay. Now, for this P plus N type of semiconductor PN junction, the total current is almost limited by the hole current, okay? Because this current, as you can see, this is the electron current, this is a hole current, and then the level of this hole current is much larger than this electron current, okay? So that is you have to understand in here, okay? I think today's we only have 1 minute, so I'm gonna come back from this slide in the next class. Okay. Do you have any question before we leave? Okay, so hopefully you guys all understand in here. Okay. Okay, then that's good. So as I mentioned, is you guys already have first homework, right? And then homework you need to submit next Monday. Okay. Okay, then that's good. And then tentatively, as I mentioned, we're gonna have our exam is March is the 15th, right? We discussed. So March 15th, we're gonna have the first exam. So I think in the next class, I'm gonna discuss more for the exam. Okay, I think that's all for today. Do you have any other question before we leave?
I know that you're going to discuss more in detail in next class, but would you be able to know the chapters that will be included?
It's probably all covers for the PN junction diode, and then the first section of the PJT. Okay.
I see. Thank you.
So yeah, let me see. Is how far we can go. Still, we have I think maybe 2 or 3 weeks. So let's see. Okay. Okay, then that's good. Okay, so if you do not have any other question, then Okay, be safe, and then see you next Monday.
Thank you, Professor.
Okay, thank you. Mhm.